In episode 26, titled 2.3 Create Better Features, Binning, Scaling, Imputation, Derived Variables, Fields, the focus is on how features translate raw data into usable signals that analysis can actually learn from. Raw data is often too literal, too noisy, or too uneven to support clear comparisons. So feature work becomes the bridge between what was captured and what can be explained. A well-chosen feature compresses complexity into something measurable, like turning a long list of events into a rate, or turning a timestamp into a time delta that reflects real behavior. A poorly chosen feature can bury meaning, amplify bias, or quietly encode future information that makes results look strong while being unreliable in reality. The aim is to build features that improve clarity, preserve interpretability, and stay defensible when someone asks why a result changed. A feature is a useful variable created or selected to support analysis, prediction, or segmentation, and the keyword is useful. A raw field like last login timestamp is not always directly useful until it becomes days since last login, which aligns better with behavior and can be compared across people. A raw field like total spend can be useful, but it might be more useful when paired with a time window, such as spend per month, because raw totals favor older accounts and can distort comparisons. Features can be original fields, cleaned versions of fields, or derived variables that combine multiple inputs, but they should always have a clear meaning tied to the question being answered. When feature meaning is clear, later analysis becomes easier to explain because each variable has a story that matches the business process. Binning is a feature technique that groups continuous values into ranges so the analysis can treat them as categories rather than as infinite precise numbers. It is often used when the exact numeric value is less informative than which band the value falls into, such as grouping ages into life stages, response times into performance tiers, or purchase amounts into spending segments. Binning can reduce sensitivity to small measurement noise and can make results easier to communicate because low, medium, and high ranges are often more intuitive than a long list of decimals. It also supports comparisons across groups by stabilizing counts, especially when the raw distribution is highly skewed or contains extreme outliers. The key is that binning should preserve the underlying pattern while making it easier to observe and explain. Choosing bins should be guided by context rather than by arbitrary equal splits, because equal width bins can produce misleading groups when data distributions are uneven. If most values cluster tightly in a small range, and a few values extend far into a tail, equal splits may place almost all records into one bin and leave the other bins sparsely populated, which reduces interpretability. Context-driven binning uses domain understanding, such as business thresholds, service-level targets, risk categories, or known breakpoints where behavior changes. For instance, a time-to-respond feature might use bins aligned to operational expectations, such as under 1 hour, same day, and more than a day, because those categories map to how the process is experienced. Bins chosen with context tend to remain stable over time, which also supports trend analysis without frequent redesign. Scaling becomes important when features operate on very different magnitudes, because comparisons and model behavior can become dominated by large-scale variables. A spend value might be in thousands, while a count of logins might be in tens, and without scaling, the larger magnitude variable can overwhelm the smaller one in certain analytical techniques. Scaling does not change the underlying order of values, but it changes how differences are expressed so that variables become comparable in influence. The educator's framing is that scaling is a way to put variables on a common measuring tape, which is especially useful when combining them into composite indicators or when using distance-based methods. Even outside formal modeling, scaled values can help with visual comparisons and with spotting anomalies when one feature's spread is dramatically different from others. Missing values need feature-aware handling because a missing value can mean not observed, not applicable, or failed to capture, and those meanings can be predictive in their own right. A practical approach is imputation plus a missingness flag, where the missing value is filled with a reasonable substitute and a separate indicator marks that the original value was missing. The imputed value preserves dataset usability by avoiding gaps that break calculations, while the flag preserves the information that something was missing, which can matter if missingness correlates with behavior or with collection bias. The chosen imputation strategy should match the feature meaning, because filling a missing numeric with 0 might be valid in one context and nonsense in another. This combined approach supports both continuity and honesty, because the analysis can use the filled value while still knowing it was not originally present. Derived fields are often the most powerful features because they express relationships, speeds, proportions, and changes over time rather than raw totals. Rates and ratios turn volume into intensity, such as purchases per week, incidents per user, or support tickets per active account, which allows fair comparisons across different sizes of entities. Time deltas turn timestamps into behavioral measures, such as time since last activity, time between sign-up and first purchase, or time from incident detection to containment, which better reflects process performance than raw dates. Derived variables also help standardize across uneven observation windows, because a 2-year customer and a 2-week customer can be compared using normalized features rather than absolute totals. The discipline is to keep derivations simple enough to explain and to ensure each derived feature has a clear unit and interpretation, because unclear units create confusing results. Leakage is a feature risk that can make an analysis look impressive while being untrustworthy, because it occurs when a feature includes information that would not be available at the time a decision is made. A common leakage pattern is using a future outcome, or a proxy for it, inside the feature set, such as including a cancel date field when predicting churn, or using a refund code that only appears after a customer has already left. Leakage can also appear through aggregation windows that extend beyond the point of prediction, such as calculating support tickets in the next 30 days as a predictor for churn, which is not a predictor but a consequence. The safest mindset is temporal discipline, meaning every feature should be evaluated by asking when it becomes known and whether that timing matches the analysis scenario. When leakage is removed, results may look less dramatic, but they become far more credible and usable. A churn example ties feature creation to outcomes because churn is a behavior with multiple causes and multiple signals that can be captured as features. Churn can be influenced by declining engagement, rising friction, unmet expectations, and competitor pull, and those drivers often show up in measurable variables like days since last login, drop in usage rate, increase in support contacts, or reduced product adoption. Binning might group engagement into tiers, scaling might harmonize spend and activity features, and derived rates might capture changes such as a month-over-month usage decline. Missingness flags might reveal that a certain channel fails to record key events, which can otherwise masquerade as disengagement. The main lesson is that features connect raw traces to a story about behavior, and that story should remain consistent with what the business process would allow. Feature distributions should be checked because strange spikes, impossible values, or unexpected zeros often indicate a feature engineering defect rather than a real behavioral signal. A spike at exactly 0 can mean a missing value was imputed incorrectly, a time delta was computed with swapped dates, or an identifier was treated as numeric and collapsed during conversion. A spike at a round number, like 100 or 10,000, can suggest unit conversion issues, such as cents versus dollars or seconds versus milliseconds. Distribution checks also reveal whether binning produced balanced, meaningful groups, or whether most data fell into one bin due to poor thresholds. These checks are powerful because they do not require sophisticated modeling, only careful observation of what should be plausible in the context of the process that generated the data. Interpretability matters because features are not only for prediction, they are also for explanation, and explanations are what decision-makers trust. A feature like average response time in hours over the last 14 days has a direct meaning and can be discussed operationally, while an opaque composite score with unclear components invites skepticism. Interpretability also supports debugging, because when a feature behaves oddly, a clear definition allows the team to trace it back to specific inputs and specific steps. In regulated or high-stakes environments, interpretability becomes essential because stakeholders may need to justify decisions or demonstrate fairness, and features that cannot be explained are hard to defend. Even when complex methods are used, grounding features in understandable components keeps the analysis anchored in reality. Feature creation should be tracked for repeatability and review because features are part of the data product, and data products must be reproducible to be trustworthy. Tracking includes recording the definitions, the windows used for aggregations, the bin thresholds, the scaling approach, and the missingness handling strategy, along with any assumptions about timing that prevent leakage. When tracking is absent, teams often discover that the same feature is implemented differently across projects or across months, which creates subtle drift that shows up as inconsistent results. A clear record also supports review, because another analyst can validate whether a feature's logic matches the intended business meaning and whether it introduces bias or leakage. Repeatability turns features from ad hoc experimentation into stable analytical assets. A feature checklist is useful when it can be narrated as a consistent sequence of questions that keeps feature work disciplined without making it rigid. The checklist begins with meaning, ensuring the feature has a clear definition tied to the question and a plausible interpretation in business terms. It then checks binning and scaling choices against context, confirming thresholds and magnitudes make sense rather than being arbitrary. Next, it addresses missing values with an explicit plan that preserves missingness information, and it confirms derived variables have clear units and stable windows. It then tests for leakage by verifying timing, reviews distributions for spikes and impossible values, and finally records the steps so the feature can be reproduced and reviewed later. When this checklist becomes habitual, feature work becomes safer, faster, and more explainable. The conclusion of episode 26 is to design one feature from a dataset and write down its definition in plain language before using it in any analysis. The feature should be chosen because it improves signal, such as turning a raw timestamp into a time delta, turning a total into a rate, or turning a messy continuous variable into context-driven bins. The design should include how missing values will be handled, whether a missingness flag will be created, and what checks will confirm the feature behaves plausibly after creation. The goal is not to produce the most advanced feature, but to practice disciplined feature thinking that preserves meaning, avoids leakage, and stays interpretable. When that practice becomes routine, raw data stops feeling like a pile of fields and starts becoming a set of signals that can be trusted. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.